Hello and welcome back to the Home Lab, and I've got a really interesting video to share with you today of a build project that I've just finally completed, and it's a really old form of computer read-only memory, and it's called Diode Matrix Memory. If you've been following my channel for the past year or so, you might know that I'm quite interested in old forms of computer memory, and I've made a video that you might have seen on core rote memory and another few in fact on magnetic core memory. But today we're going to look at a big build project that I've done that's on a form of memory for computers. It's very low density, that only uses diodes and resistors to store the ones and noughts. And this memory was popular from about the 1950s to the 1980s, and it's called Diode Matrix Memory. Just before we start, I want to say a huge thank you to all of you for watching and supporting my channel, and also to PCBWay, who always encourage me to make new videos, and they just let me do my thing. So I get on and make my videos, and they get in touch and say, "Oh Anthony, what are you doing next? We'll always support you with the videos you make," which is absolutely fantastic. Now, as you know, they do CNC machining and 3D printing. But if there was ever a project that would benefit from their bespoke circuit board design, this is it. Because you could get a circuit board made where you've got the diodes on it, but you could make the diodes pluggable, so you could make it not just a ROM, but a memory where you change the data in ROM. So thanks very much to PCBWay. Now let's get on and have a look at what this memory is, how it works, and how I built it. Diode matrix ROMs form a very low density memory that uses only diodes and resistors to store data. It could be used, for example, as ROM for bootloader or program code if required. It has lots of advantages. It's simple to build, fault find and repair, and on a small scale, relatively cheap to manufacture, as the same type of diode and resistor value can be used over and over again. It's also reasonably radiation hardened and generally low power too. One diode failure, however, can cause errors in the data being read through, and its data density is very low. There were ICs you could use, such as the TND903, which is just 8 diodes in a dual inline package instead of discrete diodes that you could build it with, but many examples just used individual diodes. There are also kind of blank examples that you could buy, which were fully populated with diodes, where you could remove the diodes or at least break the intersections between them that were not required to actually program the matrix. So let's have a look at a simplified circuit diagram to explain how it works using only one diode. For digital logic codes, only the states 1 and 0 are needed, as you probably know, and this can be represented by any two voltages that can be effectively differentiated from each other. Now, for the experts amongst you, you might notice that normally in these diode matrices, the diodes are the other way round, with their anode connected to the output of the memory grid, not to the input. But I've done it my way here to make it more intuitive to understand, and so the matrix outputs the correct voltages, as otherwise the output would need inverting before being passed out of the memory, which is often how they used to be configured. Right, so if you're not familiar with how these things work, let's start off with a really simple circuit so you get a good understanding of how it works, storing only one bit. So working in reverse, power supply rails here, there's the 7-segment display and its Darlington driver, but of course that could just be off onto a data bus. So that's that bit dealt with. So we need to look at this part, which is the diode matrix. So the first thing to look at is we've got a vertical wire here that has 2 resistors at either end of it and a horizontal wire here. So if you look at this bit of wire here and this bit here, that's the copper grid that I built on my model. Now, normally, as you can see, there's no connection between the address that comes in, as it were, and the vertical piece of wire here. So if we don't want to store a 1, we want to store a 0, what we do is we don't energize this line. It's not connected to anywhere. We don't put a diode in, and so the 7-segment display gets a 0. Now, why does it get a 0 if this diode isn't here? Well, if you can see, power supply rails there, a very high value resistance at the top and a low one at the bottom. So you need to know a little bit about potential dividers, but the biggest resistance always has the biggest voltage across it if they're in series. So there's a large voltage drop across here. So at this point, in other words on this vertical wire, the voltage will be way lower than 9. It'll basically be almost 0 because this is only 220 ohms. And I've written current limiting. It has that sort of effect as well on the diodes when we put them in. Anyway, without a diode, the voltage on here is very, very low because most of it is lost across this 820 kilo ohm resistor. So what would go out along here, if you can imagine 0 going out, is no voltage, and therefore the segment on the 7-segment display is not lit up. Now, let's put a diode in. Now, normally you'd use a very small, tiny, to make it dense, signal diode that has a very low voltage drop across it. As I said, I've used LEDs so you can actually see how the data flows. So if we want to send a 1 to our 7-segment display or out onto our data bus, then we need to connect between this line that's coming in and the vertical line. Now, we do that with a diode, and the effect of this diode, I'm going to sort of simplify things, is to say, well, if you think about it, if a 1 comes in and a diode conducts in that direction, if there is a high enough voltage on its anode terminal, if it conducts electricity, then the simplest way to consider this diode is it behaves like a wire bringing in onto this vertical line whatever came from here. So if there's a high voltage here and the diode conducts, then there'll be a high voltage here. The rest will drop across this resistor. This point will be high, so we'll be feeding a 1 into our 7-segment display. Now you'll note which way around I put the diode. They were often put round the other way, but it doesn't matter for my demonstration because we're not going to bother then inverting the signal. So in summary, a voltage between here, which is high, and 0. But if we connect a diode between those points and we make the anode of the diode a higher voltage than is needed to cause the diode to conduct, consider the diode to basically be behaving like a wire. So this high point will be high here as well, slightly lower because of the loss of voltage across the diode junction, and we have to get that right, and therefore feed a 1 in. But if there's no diode here, there is no connection, so the voltage on this vertical wire is always 0, so that stores a 0, and putting a diode in makes sure that when we address this single bit, it comes out as a 1. Right, if you understood that, then you've earned your right of passage to look at the full circuit diagram. So it consists of about 5 different regions. Here's the positive rail of the power supply, and there's the 0. We've got a 555 timer producing pulses, which pulses to this CD4017, which switches on individual address lines. We've then got our matrix here, and I haven't drawn the diodes on. And then finally, we've got our output stage, which is our 7-segment display. So let's explain how this works in a bit more detail. So the 555 timer is a very standard circuit, and if you're not familiar with that one, perhaps have a look at that online. But I've put a little variable resistor here, so changing that will change the rate that this sends out on off pulses. And I always put a little LED in on the output pin 3 just to show that it's working, so we know that that bit is okay if we have to find a problem in the circuit. Those of you who have built these, you might know what's going on inside these and how they're laid out, but gosh, they're annoying because the pins are never in the right place. You have to have components going around the outside of it and things like that. If you built one, you'll know exactly what I mean. So on off pulses go into our CD4017, and what this does is just literally switch on one pin, then the next, then the next, then the next, and it does that through to a decade. So we go 0, 1, 2, 3, 4, 5, 6, 7, 8, 9 and back again. Now, what I've done is I've come out of that into a Darlington driver that doesn't invert, just to give us a bit more current and a bit more of a stable voltage. And I've put an LED on each one of those lines, and those are the green LEDs that you can see counting down as we address each one of these lines. Okay, there are horizontal wires and currently not connected. So if we switch this on, we'd see the LEDs switching on down here, one after the other, but we would have everything off on the 7-segment display. Here's our potential divider with the high value resistor here. So currently, if we don't connect between the horizontal wires and the vertical wires, then the voltage on these vertical wires is low because most of the voltage is lost across this high resistance. So a low goes into the segments of our 7-segment display and nothing lights up. So what we're going to do is connect diodes between each position where we want a segment turned on for a particular letter. And if you remember, the first horizontal row across here is going to be the F, J, and then we spell out physics down here. So if we need to light up an F, we're going to have to get that segment, that one, and that one lit up. So for those positions on here, we're going to have to put diodes in, and those diodes will conduct. And if they conduct, they will pass the voltage across onto the vertical wire. So it's now connected across, and that voltage will go into our 7-segment display and light up the segments that we require. Now, the really observant amongst you might notice that I'm using 2 different kinds of Darlington driver here. There's a bit of a reason for that, and it's nothing to do with the array. This one is a sort of straight through one. This one is rather different, but the reason for that is we actually need to make these points 0 when we want them on, so it sort of inverts. And the reason for that is this big display that I've got is a common anode display. So that's a little bit technical. Normally you wouldn't need an inverting Darlington driver, but it's because all of these segments are connected to the positive all of the time. So what we need to do is drag them low when a high comes in. I hope that makes sense. Finally, one or two of you again might say, get yourself a CAD program and get drawing properly. I'd be interested to see what you think in the comments. I personally find it much easier to see hand-drawn circuits if they're drawn reasonably well, and I'd like to think that this is drawn reasonably well. And I use lots of colour to make different areas more visible. You might disagree with me. I mean, it's one of those things, you either like it or you don't. But I certainly find drawing it like this, I not only understand it better and seem to make slightly less mistakes, so there's a bit of Tipex here and here. They're often where I've added to the circuit as well. But I just find, to me, the layout is more clear. But you tell me in the comments if you think if they're drawn on a computer printout, they're clearer. I'm not sure, but at least it all fits onto a piece of A4 paper. Once I'd decided what text I wanted to display, FJ's physics being the obvious choice, I sketched this out to show, ignoring hyphens, apostrophes and spaces, that I needed 10 letters. Therefore, the memory would require 10 lines if each letter was to be shown after the previous in order. I could have got away with using just 8 lines, as there are 3 S's in this text, but it was easier just to have 10 lines, 1 for each letter in the sequence of FJ's physics. I drew out how I wanted the letters to look on a 7-segment display and began to draw out a schematic. I needed a truth table to know where the diodes were needed on the diode matrix grid and where they weren't. As I wanted the diode matrix to look separate from the rest of the electronics, I designed it as a separate block, which I suppose could be interchanged if a different program was required. Because I used LEDs to show how the data travelled through it, the design was slightly more complex, and it took me a number of iterations on paper to get the construction details correct, with all the terminal strips that were needed and the connection to the LEDs and the various resistors. But I got there in the end. So it was out to the garden to do some cutting. And as you know, I find these desktop bandsaws absolutely fantastic. If only you could change the blade easily, or how about having teeth on either side? Have you ever done that? So you could turn the bandsaw around and run something through the other way. That would make life a lot easier. It would almost be easier to own 2 bandsaws with different pitch blades fitted, though I'm sure I haven't got the storage space for that. I particularly like these small desktop drill presses. It takes up so little storage room and accepts a drill size up to 7mm, which is much more than my Proxon Dremel style one. Barry watched in a close but safe manner, as I feel that these things are great skills to share with your children if it's safe to do so. Barry also proves to be very helpful at cleaning up. I particularly hate the swarf that this sawing and drilling produces, especially when I'm doing it indoors. So, as you might know, a good hack to minimise this is not to draw directly on the workpiece, but to use a paper template. This has the effect of containing a great deal of swarf until you remove it, which I find helps a lot with the clearing up. With most of the holes cut out, it was time to fit lots of brass standoffs and solder tags to hold the structure of the grid's XY wires. It was then time to build the circuitry that sends the pulses to the diode matrix to address its data and for the output 7-segment display with its Darlington driver. You might know already that I'm a huge fan of these very cheap circuit board holders, which just make construction of the circuit you're doing so much easier. One tip, or they seem to be called hacks these days, is to use some masking tape to hold any of the components still that might move when you invert the board for soldering. I always enjoy the stage when you get to select the ICs and fit them into their sockets. I'm particularly pleased to use some of these from this box. I've had many of these since I was a teenager and they still work perfectly. With the circuits built, I then worked out where to place them on the A3 piece of perspex that acts as a base for the whole project. For ease of wiring and more importantly explanation, I decided to remove the 7-segment display's Darlington driver chip from the 555 timer and 4017 board and mount it onto the board that had the large 7-segment display directly on it. Not sure why I didn't do this at the start, as it seems much more logical in terms of layout. But it was at this stage it all went wrong. Try as I may to get this really simple circuit working, continuity checks just failed every time I tried them. Even with no components other than the sockets and some limited wiring on the board, the problem just persisted. After much desoldering and resoldering and checking my joints for shorts under the desk lamp lens, a small glint caught my eye. There was a tiny bridge on the original Vero board tracking. Well, I guess you pay for what you get, but it's another salutary reminder that when things fail, check the simplest things first and take nothing for granted. Having sorted out the layout, there was a lot of wiring to do. I needed to make a grid of copper XY wires and then solder on 43 red LEDs to act as both the data ones and as data indicators. Once this structure was complete, it was time to solder on the diodes, resistors and some extra LEDs with their current limiting resistors just to show which line was being addressed. I made sure I got these in the correct places with regular testing along the way. The other 10 green LEDs down the left side of the matrix are the address line LEDs, which give a visual indication of which line is currently being addressed by the CD4017 decade counter chip. All this soldering was a slow and laborious process, but as with all these kinds of builds, you can see the progress you've made as you continue to build. It was not easy to remove the protective film on the diode matrix board, but it's always worth leaving on for as long as possible. Once removed, the Diode Matrix ROM could be seen in all its glory. Okay, so here it is, the diode matrix memory. Now that took rather longer than I thought to build, but I'm really quite pleased with it. There's a few connections obviously that need to go to the external circuits, but the thing to appreciate is the letters that I want to display are now hardwired into these diode positions, and unless I unsolder them, that data can't be changed, so it's a read-only memory. And so what I need to do now is bring it in with the other circuits and then start to wire it in so we can get it working properly. But what I thought might be interesting to mention is, of course, if I want to display something different on the 7-segment display, then I could put this on sockets or plugs, and I could remove this bit of memory, and then I could put in another one and run something that's completely different. I now needed to wire up the 10 address lines and 7 data bus output lines as well. I could have used ribbon cables for this, but as I did with my core rope memory build, I rather like using coloured single strand wire to do this, as it seems more indicative of the path the data is taking. As ever, I did regular testing along the way to make sure that everything up to that point was working. A good idea actually, because often I found that I'd made some silly errors that needed correcting. With it all finally put together, I found that it worked, but the 7-segment display was not lighting up, as the voltage drop across the LEDs on the matrix board was just too high, in fact much higher than it would have been if I'd just used regular diodes. So, in a reversal of what I'd done before, I added another Darlington driver to the input stage of the matrix board. I needed to drive 10 lines, and the Darlington ICs only have 8 channels, so 2 chips were needed. After that addition, it all worked really well. Finally, with all this done, rather than using the desktop power supply all the time, I added a PP3 battery holder to finish the project off. I always love that final stage when you remove the remaining protective film on the perspex and you can see the fruits of your many hours of thought, planning and hard work. So I turned it on and it was completely dead. It's only at these stages do I realise just how resilient I am. Following the adage of check the simplest bits first, it turned out to be that the cheap PP3 battery holder had a negative wire crimped to the negative battery post with the insulation still in place. So I repaired that, and at last I had a working Diode Matrix ROM memory, which not only shows which address line is active, but also has LEDs that indicate which diode is conducting to pass a digital 1 or on pulse to the 7-segment display. Overall, it came out a bit larger than I wanted, and I took longer than I'd expected to build it, but I am, in general, pleased with the build, and I hope you are too. So let's have a quick look at what I've built. Well, I've been wanting to build a project like this to show you diode matrix memory for quite a long time. And I thought, well, what can I do? And the obvious thing to do was to build a matrix that would control a 7-segment display and spell out letter by letter FJ's physics. So in a minute we'll have a look at the circuit diagram and actually how these diodes transfer data. But just to give you an idea of the full build project, what we've got here is our normal 555 timer, and there it is ticking away. And then we've got our CD4017 chip, and all that does is decade count. So you can see it counting down here. So that's coming in off this board. It's going via a Darlington driver just to give it a little bit more current and make the voltage a bit more stable. So you'll see it counting down. There we go. And we sort of consider it starts at 0, 1, 2, 3, etc. Now, the next bit is a whole series of diodes on a normal memory that uses diodes. I've put LEDs in because LEDs can actually indicate the data flow, so you can actually see them lit up. So as you'll see, we go down here, you might notice a couple of rows that are identical, and they're the program for the letter S. So what we've got here is 7 vertical lines, and this is the A, B, C, D, E, F and G segment, A, B, C, D, E, F and G segment of the 7-segment display. So when we switch on a line, we have diodes going across here horizontally, and those diodes are in positions that indicate a 1. And if there isn't a diode, it's a 0, so that segment of the 7-segment display doesn't light up. So we then come out from those diodes, and again we come out on the bottom here, and there's either a high if there was a diode and a low if there wasn't one, and that goes again via a Darlington driver just to up the current and keep the voltage a bit more stable to our 7-segment display to light all of the segments. So I hope that makes a bit of sense. In summary, individual pulses coming in here, those pulses go to a row of diodes, and those diodes are positioned in such a way that if they're on, it's a 1, and if they're missing, that segment doesn't light up. And then off we go via a bit of a boost here to the 7-segment display, and it spells out letter by letter FJ's physics. Now, as ever, I hear you say, FJ, get yourself a 3D printer. Well, I kind of wish I had one. I'm not sure I've got the space for it, but I'm sure I could make some space for one. But I do particularly like the hands-on way of making things first, because you get a real feel for how they work, and you can sort of sort out all the problems in advance. But I think if I made another one of these, I would 3D print bits of it. And of course, what I would do is get a bespoke circuit board made to make it a little bit more permanent. But anyway, I hope you like my sort of knock it together build. At least it works really well. Just before we finish off, let's have a look at some statistics for the Diode Matrix ROM that I've made. So it stores 70 bits or 70 ones and noughts on a 10x7 grid. And it's got a surface area of about 0.024 meters squared for what is 8.75 bytes. Now I know it's 7 across, but let's assume there's 8 bits in a byte. It weighs in total, so that's the whole thing, 940 grams, and I forgot to weigh the diode matrix part before I soldered it all together. So let's just assume that it's about a quarter of this, so about 235 grams for that part of the construction, which is 0.235 kilograms. Right, now we've got that data sorted. Let's build, or assume we're going to build, 1 gigabyte of diode matrix ROM. So 1 gigabyte is 1,000 million bytes, divided by 8.75, so that's our little circuit. That would be 114 million of these grids. Now, with the mass that they've got, that would be a mass of about 27 megatons. And if you work out the surface area, a surface area of about 2.7 kilometers squared, which coincidentally comes in at about 10 megatons per kilometer squared. Now, I thought we'd work out how much this gigabyte of diode matrix would cost us. Now, I'm not quite sure how much mine cost, but I had to buy, just for the diode matrix part, I had to buy the perspex, the brass standoff, solder tags, solder, bits of wire, copper wire, etc. So let's assume that it cost me about £20. So the cost per gigabyte would be 114 million times 20, which is 2.3 or thereabouts billion pounds. So I don't think we'll be making a gigabyte of this kind of memory anytime soon. Well, if there was ever a project that fooled me, it was this one. I thought it was going to be a really quick demonstration and quick build to show you how the diodes form little data bits on the diode matrix memory. But it took ages and ages to build, and in fact I think it took me longer probably than any of the projects I've done to date. But I got there in the end, and I suppose you kind of form a relationship with projects that you make, and I've really enjoyed all my other ones. And this one, I was beginning to lose the love for it because it was just taking night after night and all my afternoons. But got there in the end, and it works really rather nicely, so I'm very pleased with it, and I hope you've enjoyed it as well. Anyway, If you've enjoyed the video, do consider liking it and subscribing if you'd like to. But most of all, please leave a comment. I find that section the most interesting because you've all got extra stuff to add, and the knowledge that you have is way beyond mine quite often, and you've had some really interesting stories to tell. So stay with me till the end of the video. As you know, I cut in a few extra bits after I finished so you can see other bits that didn't make it into the main body of the video. But whatever happens, I'll be making another video soon, and I do hope you'll join me then.